years ago, and he said, "What do I do to get my thesis done in 4 years?" And I explained it to him, and he said, "Okay, I'm going to try." And so he hasn't finished his 4th year yet. So I think officially we'll sort of call it 4 years, maybe. if we can get done before the fall of this year, which is when his 5th year will actually be over. So with no further ado, I think Darrell's got a good talk to give us. I think he'll put it in, a lot of these very specific technical questions he's dealt with in some good perspective. He's somebody who spans the disciplines, maybe as much as any student I've ever had, who is very, very strong technically. He came with a mechanical engineering background, came working in aerospace. You'll hear a little bit about that. And he adapted very well to the biological application domain, but very strongly kept a firm basis in the technical. And so I think you'll see a really good combination of strong technology applied to what I, of course, think are the most compelling biomedical problems we could be dealing with today. And that's of the heart, of course. So with no further ado, Darrell.
All right. Hey, thank you, Rob, for that introduction. And to start off, I wanted to give a little of my own explanation of why I chose to do subject-specific modeling. And so, all right. Whoa. A little bit of a delay there. Preview. So before I came to the University of Utah, I worked in aerospace. And this is the F-119. This is an engine I worked on at Pratt & Whitney. And this is for the F-22 Raptor, which is a really cool jet if you're interested. But anyway, while I was here working on this project, I learned 2 really important lessons. First is that in this context, computational models are extremely important. They put a lot of emphasis on their modeling techniques. In fact, they make multi-million-dollar decisions based on some of these simulations. In fact, the reason I think they can do this is because they have spent decades validating their models directly to the real thing. And they've come up with very strict methodologies that enable them to have confidence in their models and know the model's limitations. And while I was working at this company, I worked on a specific analysis called a backbone bending analysis. And this is where you take the cases and the frames of the engine and you apply flight loads. And you see how much the engine deflects. And the idea is to see how much clearance you have between the spinning parts and the structural parts. And ironically, while I was working on this exact analysis, my mother was in a car accident where she fractured 4 or 5 of her vertebrae. This isn't her, fortunately, but the doctors wanted to fuse her back together in multiple places, but they were worried about the load-sharing issues that this would cause. And they didn't know what to do or how to proceed. And I was shocked as an engineer that they didn't have a single computational tool to help them make this decision, not even a rudimentary tool. So when I came to the University of Utah, I quickly became interested in electrophysiology. And a lot of this is because of a lot of the modeling aspects. I could get scans of patients and different subjects and quickly generate computational models. And I could do this for make simulations of different diseases. In particular, one disease that we'll talk about a lot today, myocardial ischemia. And I learned that very quickly, early on, that these simulations weren't considered very accurate. Not my models or simulations, nor the ones I saw in the literature. And this is because they hadn't done their due diligence to validate some of these full body level simulations back to the original thing. So this soon became the focal point of my PhD thesis, where I take experimental data and I create simulations based on this experimental data and then validate it back to the original thing. And this way I can create methodologies and techniques that allow us to have much more accurate simulations. And in order to understand all the details I'll tell you, I need to start by giving you a background in electrophysiology and then some of the methods that I used. I'll have 3 projects. The first is a border zone project. This is a physiological assumption. Then we also have modeling assumptions, and this is in the form of conformal meshing. And then the third project deals with the uncertainty that is over the entire pipeline. And then will be a short conclusion and future work section. So to start off, we have to understand how the heart works. And we all know that it's a muscle that contracts, that pushes blood throughout the rest of the heart. However, what's often overlooked is that it's actually controlled by an electrical wave that propagates through the heart, coordinating and synchronizing its contraction. And many of the diseases we see in cardiology are electrical problems rather than mechanical problems. So in order to understand these diseases, we have to look at the basic mechanisms through which the heart conducts electricity. And here we go to the cellular level. Here are cardiac myocytes, the cells of the heart. And you see that they're long cylindrical cells connected end to end with one another. They form these long strand-like structures. And on this side, you see this in 3 dimensions. If I were to draw a schematic of this, it would look something like this, where you have this is just a schematic of 2 cells where they're brick-like structures connected end to end. And between the 2 cells, there's channels known as gap junctions that allow molecules to pass from the intercellular space of one cell to the intercellular space of another. And when we talk about electrical conduction in the heart, we're talking about the flow of ions. Okay, great. Okay, so when we're talking about electrical conduction of the heart, we're dealing with the flow of ions, positively or negatively charged ions rather than electrons. And in the cell, there's primarily 3 types of ions that we deal with. Potassium, and you'll notice that they're much more concentrated here inside the cell than they are outside the cell. But we also have specialized channels known as ion channels for each type of ion. We also have sodium and calcium, and both these are concentrated more heavily outside the cell than they are inside. And this is important because there's 2 types of forces acting on each ion. The first is a concentration driving force. And ions want to move from areas of high concentration to low concentration. The second driving force is an electrical driving force, where there's a voltage difference, potential difference between the inside of the cell and the outside of the cell. And this is known as the transmembrane potential. And the summation of these 2 driving forces is what determines whether the ions flow into the cell or out of the cell. And when they finally come to rest, this whole system comes to rest, most of the ion channels are closed, and it's at a potential value, transmembrane potential of negative 87 millivolts. But what happens if each one of these cells is able to produce what's called an action potential? And when an external stimulus is applied, either naturally or artificially, you see that the transmembrane potential is elevated, which causes the voltage-gated ion channels, first the sodium and then the calcium, to open. And this causes the ions to flood into the cell, greatly increasing the transmembrane potential, at which time the sodium ion channels close and the potassium ion channels open. And because of the very high concentration gradient, the potassium ions flow the opposite direction, and while the calcium ions continue to flow out of the cell. And thus you see this region here known as the plateau phase, which there's very little change to the transmembrane potential. And then after a short duration, the calcium channels close and the potassium ions continue to flow out of the cell, pushing the transmembrane potential back to its resting state. And in this way, this is the mechanisms behind an action potential. However, during this whole time period, ions are free to flow across the gap junctions. So when the ions begin to flow into the cell, they also flow across the gap junctions and become the stimulus for subsequent cells to launch their own action potentials. And in this way, excitation propagates cell to cell like a domino effect. And if you look at it from a tissue level, it's like a wave that propagates across the myocardium. And many diseases have their underpinnings in some of these cellular ionic concentrations or changes to ion channels. So to understand these diseases, we've had to come up with mathematical models. And the first people to do this were Hodgkin and Huxley, who subsequently won the Nobel Prize for their work. And you see that they modeled the membrane dynamics using a representation like this, where you have 3 components. First is a cellular a capacitance component. Second, you have these voltage potentials, or these driving forces. And this represents the electrochemical gradients that I told you about earlier. And the third is these resistive elements. And now, these represent the ion channels. However, the problem with this is that ion channels are highly nonlinear. So they had to come up with a way to model this nonlinearity. And initially, they just had simple models where they had just an open and closed state, but more contemporary models use multiple state Markov models, statistical models, with open, closed, and inactive states. And from these Markov statistical models, we're able to derive ordinary differential equations. And typically, they're based on what are known as state variables. So they're functions of time, transmembrane potential, and concentration of particular ions. And here is a more contemporary model. This is the Faber-Rudy model, and this is actually the model I use in many of my simulations. You'll notice that there's dozens of ion channels now, and there's even this internal calcium handling mechanisms. And now if we wanted to model a single cell, this would be great. Or if we just wanted to do a few cells, these models would be perfect. However, the heart has over 4 billion myocytes. So in order to, we can't model dozens of ion channels with multiple state variables for 4 billion cells. So we have to come up with a formalism that allows us to do this, and this is known as the bidomain. And the bidomain equations, they model the extracellular space and the intracellular space as continuous domains, where there's some conductivity associated with each domain. And because of the unique structure of the myocytes, because they're elongated and they have these gap junctions in between, they have a highly preferential direction of conduction. And this creates large anisotropies in these two different domains. And between the two domains, we still have a model of the membrane. And in this case, it's the same as the models I showed you before, but in this case, it represents an aggregate of cells rather than a single cell. So if we take and write out the equations for each domain in 3 dimensions, we see that we get Poisson's equations, where on the right-hand side, we see any current flowing into one domain has to flow into the other domain, or has to be leaving the other domain. And by definition, the difference in potential is just simply the transmembrane potential. And if we bring in a fourth equation from our cell model, we now have all the equations that form the basis for the bidomain. If we rearrange these equations algebraically, we start to see that we can solve for the transmembrane potential, and this is very useful for many researchers, but we have to do it in terms of the extracellular potential and the ionic membrane currents. And if you remember, those come from our cell model, which is dependent on the transmembrane potential, as well as we have to solve for the extracellular potential, which is dependent on the transmembrane potential. So this becomes a parabolic equation that we have to solve over time using initial conditions. And to do this, we use an iterative integration technique, one of which is Ford-Euler's method, where we solve using initial conditions for the transmembrane potential. We can then plug it back into our cell model and our extracellular potential equation, and then feed those back into our iterative method. In this way, we solve for the transmembrane potential and the extracellular potential for the entire time domain of the cardiac cycle. And to give you a perspective, this is very computationally intense. If I wanted to solve for a full human heart over one cardiac cycle, on the biggest machine we have here at Ski, this would take me around a month to solve, and it would create terabytes of data. So there's a lot of advantages to simplifying this, making approximations. And one approximation that researchers make is known as the static bidomain, where in this case, we just solve for one single time instance. And in order to do this, we need to be able to approximate this transmembrane potentials. For many diseases, we can actually do this. We can take experimental data and approximate the changes in the transmembrane potential. One disease that lends itself really well to these types of approximations is myocardial ischemia. And this is what we sought to do in our research. So what is myocardial ischemia? Myocardial ischemia, the simplest definition, is an imbalance between the supply of oxygenated blood and the oxygen requirements of the heart. So you can cause this by coronary artery disease, where there is a blocked artery that feeds part of the heart, or through a compromised vascular system where you have an increase in demand. And while these pretty much are seen as a perfusion problem, they have large electrical consequences. Primarily, if we were to take and measure a single point on the heart, we'd get what looks like a normal action potential. Now, if you were to shift that point that you're measuring and measure a spatially different point on the ventricle, you see that you get a very similar action potential. However, because of this, they're shifted in time slightly, but because of this long plateau phase, there's a time period at which the potentials between the two spatially different regions are very similar. And so at this time point, there's no potential difference, so there's no current flowing. And if you look at this from the perspective of a remote electrode, such as an electrode sitting on your surface of the body, what you get is a spatially averaged signal over the whole cardiac cycle. And that time point that I'm referring to, where all the myocytes in the ventricles are at the plateau phase, corresponds to this segment right here, the ST segment. And because there's no current flowing, you see that there's no potential or very little potential during the ST segment. Now, if you have an ischemic region, it has some consequences on the action potential because it increases the extracellular potassium. It also increases metabolic waste products within the cell. You start seeing an increase in the resting membrane potential and a decrease in the action potential amplitude. Because of this change, you now have, at that plateau phase, you have a potential difference causing currents to flow. These are known as injury currents. These injury currents manifest themselves on the ECG as either elevations or depressions during the ST segment. And this is one of the most classic markers for myocardial ischemia. However, particularly in the case of ST depression, these are not extremely accurate markers. They're only about 68%. The sensitivity is only about 68%. And the reason for this is we don't fully understand the details of how these injury currents form. Why in one case, when you have a fully developed ischemic region, would you get an elevation, versus when it's only partially formed, would you get a depression? And this is one of the questions we seek to better understand with the intention to improve the ability to diagnose myocardial ischemia using ST elevations and depressions. And this is kind of the broader research of Rob's group, and so we work as a team on many of these steps. Particularly, we have an experimental pipeline where we're looking to understand experimentally how these currents form. Then where I focus more is on this side of the pipeline, where I'm able to create subject-specific models to try to simulate these injury currents that form. And then I can actually take these models and compare them directly to the experimental data. And in this way, I'm able to validate a lot of our modeling techniques. So briefly, I'd just like to explain each side of the pipeline. The experimental pipeline, we induce ischemia in a large mammalian heart, such as a dog or a pig heart, by controlling the flow of blood into one of the major arteries. And we also control the demand of the heart by pacing the rate of the heart. In this way, we control both the supply and the demand of the heart. And we can create all sorts of types of ischemia. We then instrument the heart with different types of electrodes. The first type is what you see here. This is known as a torso tank. It's a tank in the shape of a human torso filled with electrolytic solution that approximates the conductivity of the human body. And we submerge these hearts into the torso tank, and we're able to record potentials on the torso surface. We also equip the heart with what are known as sock electrodes. This is literally a nylon sock where we've stitched 247 electrodes onto it. And this allows us to record the surface potentials, or the epicardial potentials, of the heart, as well as we put up to 45 plunge needle electrodes. Each needle has 10 electrodes, and we put them into the region of interest that we're going to make ischemic. And we can now record potentials throughout the wall of the heart. And we use a custom acquisition system. And we could not do all this work without the help of the people at CVRTI. They are very important in helping us with the animal preparations and the instrumentation that we use. And once we have this data, we can then take and create models. And the way we do this is actually that we first collect a lot of data. And a lot of this is with the help of, I see a lot of them here, of the people from the small imaging scanner at Cheese Group. And we take and we collect MRIs, diffusion tensor data. We record the location of all the electrical electrodes, as well as we take CT scans. And at times we'll take and use contrast agents to identify different regions of the heart that are of importance to us. And so we have all this data acquired in different coordinate spaces. So we have to take and register it all together. And most of this is fairly straightforward. We use linear correspondence-based registration techniques, such as a Procrustes algorithm, to register the DTI to the MRI to the CT scan. However, there are some more complex registration problems that we have, such as the SOC, which is elastic, and it changes between experiment to experiment. And we have to use nonlinear methods. I've actually implemented a thin plate spline morphing algorithm in SkiRun to morph the SOC onto the heart geometry. And this way we get them all aligned in the correct coordinate spaces. And from there, we use a tool that we developed here at Ski, Seg3D, to identify every tissue of interest. In our dog experiments, these aren't too hard of a segmentation problem. But in other experiments, you see that there's multiple tissue types that you have to identify. And we can do that creating these label maps with Seg3D. Those label maps feed directly into another program. And this is actually work that was started based on the thesis of Mariah Meyer. And it's a project of both Chris and Ross. And I've been working on this team ever since I got here to Ski. And what this program does is it takes and it puts particles over the surfaces and interfaces of these label maps, and it optimizes their location such that we get very accurate descriptions of these interfaces, and these particles are very well spaced. And from this particle optimization, we're able to create surfaces. And then once we have these surfaces, we can fill them with tetrahedra, and we use a Delaunay tetrahedralization method, primarily through a package known as TetGen. Once we have the underlying structure constructed, we can apply conductivity values. And we do this using the diffusion tensor data. We convert them to conductivity data through literature values, where we create conductivity tensors and apply them across the finite element mesh. Now, this kind of concludes the modeling aspect of what we've done, and we're now ready to simulate different diseases. And here you'll see one of my models where I have myocardium, a blood volume, and an ischemic region. This ischemic region was determined from the experimental data by thresholding the potentials of the plunge needles, so that we threshold out the regions that are elevated to represent the ischemic regions. From this, we can apply the static bidomain equation and calculate the potentials in the extracellular space, and particularly on the epicardial surface. We can then take this and compare these epicardial potentials directly to the SOC data that we collected experimentally. Yeah. Well, during the experiment, we induce ischemia and we record it with the electrodes. And then, yeah, we control the flow of blood into one of the arteries. The needle electrodes. And we assume that there's a strong correlation between electrical elevation and actual ischemia. It's not necessarily exactly the same, but it should be pretty good. Yeah. Mm-hmm. No. Particularly in ischemic regions, there's a lot of changing that goes on depending on the state of ischemia. And we use some work done by Jeroen Sinstra to calculate these tensors, and I can point you at that work if you'd like. And it's important to know we're not the first group to do this type of modeling. This is the Simula group in Oslo, where I almost went to work, but this is Kilpatrick's and his group, And then some of his contemporaries, Lee and Johnston, they all put together these models based on the static bidomain. Most of these models, especially this one and this one, were not derived from actual geometry. This one here is my predecessor, Bruce Hoppenfield. His was based on the Auckland heart geometry, not necessarily subject-specific. And these all kind of have a lot of similar assumptions that they're based on. And these assumptions actually come from infarct data rather than from ischemic data. And an infarct is different from ischemia in that after you've had ischemia for a while, these cells start to die. And after they die, they start to form scar. And this is nice because you can then take the heart and look at it and do histology and see, oh yeah, there's the region we're looking at. Whereas ischemia, you can't do that nearly so easy. So what they saw in the infarct data is you see these stained regions, and there's this kind of abnormal boundary between the infarct and the healthy region. And you do see in the MRI that it's a very sharp, distinct boundary. And so for all these models, they all said, okay, our ischemic region is going to be a very homogeneous region in potential, and there's going to be a very sharp boundary between the ischemic region and the healthy region. Now, there's a lot of reasons to believe that ischemia would act different from the infarct data. And so one of our main goals was to take and to validate the literature-based transmembrane profiles of static bidomain models by utilizing subject-specific models to compare with experimental data during acute ischemia. So what we mean by this is I talked about the static bidomain, and there's this term here that we need to approximate. And here's the approximation that many of these other groups have made. They say ischemia, it's about 30 millivolts different than healthy tissue, and then there's this border in between. We don't know much about this border. It's either a sharp linear function, or maybe if we get really fancy, we're just going to blur it with a Gaussian function. And most people have used a fairly sharp transition, like I said, due to this infarct data. But there's some also research from Factor and Kirk on perfusion beds that suggests that this should be a sharp border as well. However, if you look at some of the experts in ischemia who are studying ionic concentrations, they would suggest that it should be a much more diffused border. They see a lot of diffusion in the ionic concentrations. So our question was, first of all, how much does this parameter even matter? How sensitive are our simulations to how we model this border region? So we fit a Gaussian blurring function to this, where we could change the variance of the equation in order to change the width of the border. And we wanted to see how this affected the potentials on the epicardial surface. And this is what we found. And particularly in this region, we see that they're very sensitive to the width we choose for our border zone. And this just so happens to be the same width that most of these models are created in. This is around 3 millimeters border zone. And this is exactly they usually create these models with a 2 to 3 millimeter border zone. So yeah, this is a very important parameter. So the next question is, well, what's the right width? Like, how should we model this border zone? So we took and we looked at some of our simulations, and this top one is from a very early stage of ischemia. This bottom one is from a more full ischemic region. And we look here, and you can see these very focal depressions. And in this model, we have a very sharp border, and same with this one as well. And we get these very sharp focal depressions with high magnitudes, much higher than what we actually see in the experimental data. Yes?
For this simulation, what is your resolution of for the
These have on the order of 1 million elements.
resolution, millimeters?
Oh, millimeters? They're just under a millimeter for the edge length.
Because your variance of
Or-
millimeter that is also very much dependent on the resolution of your simulation,
Right,
of how well you can quantify that.
right. And that you're definitely right. And particularly in our next study, we started looking at the mesh aspects to doing this. And we do see that at some point there's some errors when you don't include enough resolution. And we kind of varied the resolution to find a resolution that actually works pretty well. I think, if I remember right, this actual simulation was on the order of, they're close to a millimeter width, I think. So anyway, you do see these high magnitudes, but Strong's absolutely right. How you create the mesh under this makes a big difference in what you see. Then when you make a smooth border zone, you actually get a much more diffused depression region. And actually, in this case, it's much lower than what you see experimentally. And in many other cases, too. This one actually matched, it just so happened, but in most cases, it was lower. So one other observation we made is, if you look here, this is kind of our ischemic region. We don't see the gradients that we see in the actual data. So we went back to this assumption, and we said, we don't like this assumption that it's a uniform plateau ischemic region that has this transition. Instead, we included what we call a transition region, where instead of being a plateau, the ischemic region transitions throughout. And then at the end, we created this nice sharp border zone to give us these nice focal depressions. And so we essentially fit a function to best simulate our data. And here we see that we get much closer matching gradients within the ischemic region, and actually the amplitude of the depressions and elevations matched much closer as well. And what we learned from this study is that modeling ischemia with the notion that it's much like a plateau is incorrect. A much better approximation would look something like this, where you get a much more dynamic, where there's peaks, and depending on the direction in which you travel, you get either sharp borders or you get much more diffuse borders. So it's a much more complex process, and that it's a very important parameter to get the right simulations. And going back to Sarong's point, we started thinking about, well, this is a physiological assumption we're looking at. But what about the geometric methods we use to approximate these boundaries? How important is the underlying structure in this approximation? And you see here, we have this term here, the Laplacian operator. We use finite elements the Glerkin method to approximate this stiffness matrix. And so we have to look at some of the details on how we tessellate our domain and approximate these boundaries in order to see what kind of errors we're introducing. And this becomes really important in biological tissues. And that's because you see here, this is a rabbit leg. And here I just have 4 materials. Yet, even with these 4 materials, I see multiple internal boundaries, where here you see the boundary of the bone. And you see these points here where maybe multiple materials meet. And at these junctions where multiple meet, these interfaces become very complex. And a lot of algorithms that tessellate this domain in a mesh, they have a very difficult time accurately representing these interfaces. So what they do is they either approximate the interface, or they simply ignore it and deal with it in a non-conforming way. And what exactly do I mean by that? Program that is that it's very good at approximating these interfaces. And just like to point out, we evaluated a couple of other tools while we did this. I won't talk much about them, though, but we did look for other meshing packages as well. But what I mean by non-conforming boundaries is that if you have this boundary here that you want to represent, and you have a non-conforming method, you simply create your mesh, and then after the fact, you go in and assign the element to one material or the other material. And in this way, you have a replicated boundary, and this is very jagged. And it's not a very good representation, particularly of the smoothness of the boundary. However, in a conformal mesh, you see that the nodes and the faces are forced to align with the boundary. We're forcing the tangents to approximate the tangents of the actual boundary. And the consequences of this are that in the electrical simulations, you start to get concentrations of currents due to these jagged regions or depressions, where if you intended this to be jagged, then this would be correct. That we didn't intend this to be jagged, so these become artifacts in our simulation. And also we get these, in a conforming mesh, we have this nice smooth distribution of currents. So AIM2 was to quantify the errors from representing smooth boundaries as jagged and non-conforming surfaces in bidomain and single-domain cardiac electrophysiology simulations. So we actually did this, and so in short, how much does it matter? We did this on a suite of bioelectric problems, not just this static bidomain problem. We did 6 or 7 other simulations. However, we'll just talk about the ischemia static simulation and know that all the other simulations were very similar, except for one, and we'll talk about that. And what we did is we created both conforming meshes and non-conforming meshes, and we varied the resolution because, as Sarang said, these simulations are highly dependent on the resolution you choose for them. The errors were, and globally and locally for each type of simulation. So in the static bidomain simulations, we saw that for a global root mean squared error, that the non-conforming meshes had higher error for throughout the whole range of the resolution. And in particular, if you were to look at what's the difference in resolution for the same error, we found that this, well, I have it in terms of mean edge length, but most people think in terms of number of nodes. This is on the order of 600,000 nodes. This is on the order of 1.7 million nodes. So these are significantly coarser resolutions to get the same error. And this error is on the order of 10%. In every simulation, we found as high as 20% RMS errors down to 10% RMS errors. And probably more interesting, it was that the local maximum errors were really quite high. Here, a max error of 10 millivolts in the simulation, and of the maximum potential for around 30 millivolts, actually really quite high. But these are very local now, so within 3 to 5 millimeters of the boundary. And we see that the conforming meshes resolved quickly, whereas we always had a fairly high level of error, local error, in these non-conforming meshes. Yep.
How did you calculate the error? You had a ground truth, or it was based on a geometrical?
Yeah. So
Form solution?
no, we didn't have a closed form solution. What we did is we calculated a very high resolution mesh with the conformal solution, and we compared everything to our ground truth. And that's how we did it.
So in that case, then the conformal solution would have to go to 0 as your resolution goes.
Yes. Yes, and we also compared, there's an interesting aspect I didn't get to talk about because of time, but there's a dependence on how conformal, even a conforming surface isn't perfectly conformal, and so there's a dependence on how well these surfaces approximate the intended surface. One of the questions that they asked as we presented the conferences is, well, that's great, but what effect does this have on the full bidomain reaction diffusion simulation? Because that's a more common problem than just our static bidomain. And so that was an example of one of our simulations. And we did the same study. However, in this data, you don't see nearly as clear of a trend in the error. And when we investigated further, we found out that the errors in these simulations are much higher. And they're dependent on factors related to the meshes, such as the element size. If you had elements that varied in size, you saw very large errors between our ground truth and our other models. And this is because the propagation model is very dependent on having a uniform element size. You have to actually tune your conductivity to your element size. So these variations in element size, big deal. And actually, it was much larger error, almost an order of magnitude larger than having conforming boundaries. So our conclusions, whoa, how'd that happen? Let's skip the whole. So the conclusions were that for the static bidomain, we did see a lot of improvement. Errors typically were on the order of 10% to 20% higher in the non-conforming meshes. And in the reaction diffusion model, it wasn't as important. It actually was more important to create very uniform, well-shaped elements. And this is interesting from the standpoint of these models take a long time to construct and to simulate. So if we could get away with using, say, a structured grid, this could save us a lot of time if we don't lose a lot of accuracy doing it that way. And finally, these different simulations. We looked at both physiological approximations and geometric approximations. And we realized that for both of these, in our simulations, there were a lot of parameters that we pretended like we knew the exact value for, like these activity values. But in reality, these values change from person to person, or over time even, or during the duration of our experiment. And also geometric approximations. The body isn't rigid. Things move around inside your body. Your heart's not at one position the whole time. So what consequences do these uncertainties have on our simulations? And can we account for them? And in order to show this, we moved to another problem that we kind of leave the tissue level simulations. We went to kind of a whole body simulation. And so we're no longer using a bidomain. Instead, we're using a word problem where we have a source inside a volume conductor, and we want to see what the potentials look like on the body surface. And we're using, again, the standard Laplacian-based simulation for electrical currents, where the torso is the volume conductor. And the boundary condition is that we have known potentials on the heart surface, and on the torso surface we have a zero flux condition. And you can imagine if you move the heart around inside a volume conductor, you would get different values on your torso surface. And in reality, this is exactly what happens. Inside our body, our heart can actually swing and pivot. It's attached fairly rigidly at the base of the heart, which for you that aren't bioengineers, that's the top of the heart. And the apex of the heart can swing side to side and front to back. And so what effect does this have on the torso potentials? And we actually see this problem frequently in hospitals where someone is in a scenario where they have an ECG and they're being monitored for myocardial ischemia. Sometimes a patient will roll onto their side or sit up, and it will set off an alarm because the ECG thinks it's detected ischemia because the potentials have changed. So we wanted to find a way that would account for this type of motion, and so we could see the sensitivity of different types of motion to the forward problem. As well as we wanted to come up with a framework, so there's kind of a dual purpose on this aim. We wanted to come up with a framework for which we could use stochastic methods in our simulations. So aim 3 was to show that a stochastic method, such as the general polynomial chaos stochastic collocation method, can be applied to unknown parameters, and in this case, heart position, to improve diagnostic techniques based on computational methods. And so I start talking about stochastic methods, and I'm really talking about a sensitivity study. And what I mean by sensitivity study, because this can mean different things to different people, is that we have some parameters, and we don't actually know their exact value, but instead we can model a distribution for these parameters. We put these model, and we see that we can answer probabilistic questions, such as what are the statistical means and variations and probabilities, rather than getting a single answer. And we want to do this in a mathematically rigorous way. A lot of researchers will do kind of a brute force sensitivity study where they just kind of, based on intuition, vary their parameters. But what they don't realize is even parameters that have a linear relationship with their solutions, if you have multiple linear parameters acting together, they often result in nonlinear behaviors that can be highly unintuitive. So we wanted to approach this from a very mathematically rigorous way. And one of the more classic methods is the Monte Carlo. And this is very robust and doesn't impose any restrictions on the types of distribution. It has huge computational costs. And we found in our simulations, this was about the method that we chose was 400 times faster than what we see with the Monte Carlo. And so in collaboration with Mike Kirby and one of his grad students, Sarah Gensner, who began this project, using a technique that originated from Dongbing Xu, I hope I said that right, is called the polynomial chaos. It has an assumption that you have to be able to map your stochastic variables to a set of random polynomials, or to polynomials. And if you can do that, then you're able to use stochastic collocation to take advantage of quadrature rules to calculate means and variances and the moments. Where when I say quadrature rules, what I'm referring to is if you have a continuous integral, or a continuous function, you want to take the integral, you can do this by taking discrete points as long as you know specific locations and the weights that you need, and you take their summation, and it gives you a very accurate approximation of your continuous integral. And to set up this problem, we had to come up with a linearly independent set of parameters describing how the heart moves. And so these are the parameters that we chose, that the heart can actually swing front to back around a point on the base of the heart. And this represents kind of like when you sit forward or lean back, your heart swings front to back. And then also it can move side to side, say you were to roll over on your side. It can also shift up and down. And this is when you breathe, your diaphragm pushes your heart up and down. And then it rotates around its long axis. Every time it beats, a little bit of rotation. And these parameters, we derived the extent to which they moved from taking a subject, putting them in the MRI, and having them change positions, and then segmenting out how much the heart actually moved. And when we put these parameters into our stochastic method, we get results that are somewhat non-intuitive the first time you see them, because what we get is actually a map on the body surface of standard deviations. So we have a spatially distributed map of standard deviations for that parameter over the entire parameter space. And in this way, we not only get how sensitive something is to the motion, but the locations that are sensitive to that motion. And what we see here, this is the case of a false positive, where you have a heart that is normal. We got this from one of our torso tank experiments. And we put it inside a torso using a boundary element method and moved it around according, in this case, from a side-to-side swing. And we see that this region here, so these precordial leads, these are the electrodes that they use in the hospital for your ECG. Precordial lead 1 and 2 were highly sensitive to this type of motion, on the order of 0.2 millivolts. And that's significant in that ischemia, the threshold to determine when you have ischemia is around 0.2 millivolts. So that would be large enough to mimic ischemia in this case. Interesting enough, though, these results from postural changes, but these two here, kind of like from breathing and your heart rotating, we didn't see very large standard deviations. In fact, very little over the precordial leads. And this is somewhat reassuring that if you can just get your patient to hold still and not change their posture, you can get a pretty good, accurate signal. And because we quantify the location and the extent to which each parameter is sensitive, we could perhaps design an algorithm or change location of where we place leads to better improve our ability to detect ischemia that isn't sensitive to these motions. And we also have the case of a false negative, but I won't show you the results. They're very similar. You may not even notice a difference besides the amplitude. But it is large enough to mask ischemia as well. So in conclusion, we were able to show that it both masks and mimics ischemia, and we were able to quantify exactly how, as well as we were able to establish a framework using this general polynomial chaos. With some other work that Mike Kirby has done, we now have the ability to use these stochastic methods both in finite element methods, and this was a boundary element case, and we now have a way of doing that, which we can apply to all of our different types of simulations. So as we did these three projects, we learned about valuable lessons. One is that we found that we were working in this kind of cyclical pattern, where we take our experimental data, we learn about what geometric approximations were appropriate, and from the simulations, we learn details about things like the border zone that we hadn't noticed before, and that would drive us to go look back at our experiments and try to understand better what's going on in that border region. And then over top, we realized that these aren't nearly as clear-cut as sometimes to be, and there's an uncertainty that is over all of this, and we came up with methods to handle a lot of this uncertainty in our simulations. So in the future, I would like to continue the research on the border zone. Kind of where we're at right now is we think some of this dynamic behavior is related to the microvasculature, and we need to get better at capturing the microvasculature. And this is something I've talked a little bit about with Ed Chi and both Rob, and we want to come up with new techniques, maybe microspheres, maybe just getting better at this contrast agent that allows us to get better perfusion information. Also, we want to extend the research not just to go to the epicardial surface, but we want to take it all the way to the torso surface and validate it at that level. And then finally, after making dozens of these models, I've realized there's a huge need for us to streamline this process. This is very intense to make some of these models. So coming from the mechanical engineering side of things, I'm a big fan of parametric models. So if we were to take and use a tool like ShapeWorks or an Atlas, and we were to calculate the 6 or whatever variation of a healthy heart, we could then create a parametric model that would adapt or update to those main modes of variation. And in many simulations, this type of a model would be sufficient. And in conclusion, I would just like to thank members. This is the ischemia group right here. And then this is just people that study electrical fields in general, and these are the main people in my group. But pretty much all of you at SKI and have contributed to the software and the imaging. I see a lot of people here that have helped me in different ways. So I thank you all, and open up for questions.
I'll start things off. Very nice presentation and a really nice tour de force of all the components that are there. So throughout the talk, you mentioned a few times about different sources of error in the pipeline. If you were to characterize those sources a little bit more quantitatively, or at least in terms of largest to smallest, from the image segmentation to the meshing to the material property assignment to the simulation to the visualization,
right,
and then the analysis, where are your largest sources of error?
Perfect. I almost put a slide in here that said Chris's question, but I didn't have time. The answer to that is the registration of the needle electrodes and the registration of the sock electrodes are our largest source of error. And in this way, we've talked about, with a couple of different people, new methodologies for registering the sock and these needles. So we have an error on the order. So I did a little brute force sensitivity study where I moved around needles, and I saw that it can change the location of our ischemic region up to like almost half a centimeter, under half a centimeter. It didn't make drastic changes, but it was significant. So I'd say that is the largest area of uncertainty and where we need to focus some of our energy in doing better.
What do you think about on the computational pipeline side?
On the computational pipeline? So depends on which model you're talking about. For the static bidomain, I think we pretend like we have a handle on these conductivities, but they still are a problem, though there's been a lot of effort gone into that. And also just how we model that ischemic region, like that border zone is really sensitive. I can simulate almost anyone's data just by changing that border zone and not adjusting conductivity. So when people claim they can produce depressions of a certain magnitude, you can fit that model to make anything almost. So, go ahead.
You have to turn it on.
It's top secret.
So from a simulation perspective, I'm kind of curious to see how the cardiac and the technology will improve
Parsons, for instance,
Mm-hmm.
is there preference for meshing instead of hex? Why would you choose point of
For the electrical,
Yeah.
just in general, we're using linear basis functions in our tetrahedral, and so that's not sufficient in the case of mechanical simulations oftentimes. But we can get away. We can get away with a large. These aren't really computationally intense calculations, so we can get away with a large number of tetrahedra. So they're simpler to make in a lot of senses, and you can put a lot of them in there to represent the boundary very accurately. So that's why we prefer tetrahedra in this sense. But I don't know. There could be other reasons why you would want to put in elements. Is it? Yeah. Go ahead.
When you mentioned your dynamic simulation,
Uh-huh.
the hard geometry is changing.
Yeah. Yep.
But nowhere in your presentation I saw any mention of a dynamic geometry.
Yeah. So right now, I don't know of a group that does a dynamic update to their actual geometry. Usually what they do is they have two models that are coupled, and they have one that actually changes, which is a very coarse hexahedral grid with the higher order elements that is coupled. There's a mapping to this very high density, because we need a spacing on these nodes on the order of 200 microns. So there's really big meshes. And so they don't update the electrical mesh. And so this could be a source of error. I don't know of anyone that's actually studied the effects of this dynamic change, because there are changes that happen electrically. You have different ion channels that are like stretch sensitive. So that would be an interesting project to pursue, I think.
And the related question was, can you explain what is the approximation? Is that approximation going from the dynamic to the static?
Okay, let's go back to that.
And that's just my background, I'm pretty sure that it's
Yeah.
what are you assuming constant?
So, come on. Go. So here's the slide with the equations. So when we say static, it can get a little hairy because there's static assumptions in electrophysiology that we don't mean the capacitance static assumptions. We make those assumptions for all these simulations. What we are referring to is that we are solving this parabolic equation over the entire time series. And in order to do that, we need to know convert from transmembrane potential to extracellular potential. And so we have this equation, which is just a combination of those other four equations that I showed you. So what happens is, if we don't need to know the entire time series, or we don't really need this equation anymore, we can just use this single equation here that's a single time instant. But that requires us to know what this transmembrane profile is at that time instance. So here we start. Okay.
Okay, so this is where I had you have a superscript of time in your bottom equation.
Right.
So I'm assuming equation 1 and 2 all have superscripts of time.
No, not in the no. So if you take this equation right here, and we want to solve it over time, we use the Ford-Euler method, right? And we use an initial condition. So we say at time 0, we know a transmembrane potential, we know an extracellular potential, and we know an ionic current. That goes in to solve for time 1, or whatever your delta is, for your transmembrane potential. And then the only reason I put time subscripts here is because it's in conjunction with this equation that you put time.
I understand that, but the question that I'm having is, where is the time evolution? I mean, is there time component in that? I mean, there's no d by dt. What is the Ford-Euler is the discretization of a continuous differential equation?
Right. There doesn't necessarily have to have a time, but you have to know these currents. If you could approximate the currents coming out of the membrane, you could then do this at a single time instance, right? If you knew the membrane currents and the extracellular potentials at a specific time instance,
Then you can solve for phi.
you can solve for this. The problem is we don't know this. This is dependent on the cell model, which has ordinary differential equations that are based, if we go back a couple slides,
Your
Time.
equation
those depend on time. And so in order to solve those, we need to solve this starting at time 0, where it's at its resting state.
Call this static. It doesn't seem static at all.
Well,
It
no,
sounds like the whole thing's evolving.
So this one right here is, this one we no longer have IM in the model. We just have transmembrane potential. It's an approximation of what all these ionic currents produce.
It's an approximation because you've basically fixed IM
Be a
for that
constant.
time interval.
Yes.
For that, whatever that time instant is.
Yep.
You've fixed IM. Now you'll solve all the elliptic parts of this thing.
Exactly.
And that's why you're calling it static.
Exactly. Mm-hmm.
Not necessarily derived from
Right. So you're right. So we could do exactly what you said. We could just assume we knew at a specific time instance what the currents were, and then calculate what the transmembrane potentials were.
Is that what you're doing?
No, what we do is instead the only reason why you want to know these currents is because you want they combine together to give you transmembrane profile. So people doing research in this field, they don't measure all the ionic currents at once. You can't do this. What they do is the combination of all these ionic currents combine to form this transmembrane potential, and they can measure this transmembrane potential in tissue. And so we can now approximate the combined result of all these ionic currents as the transmembrane potential. Does that help?
Change the subject back to other numerics. When you were talking about your border zones and estimating your border zones from the simulation point of view, you have these somewhat steeper gradients around the border zones. How do you take care of that numerically? Do you do any adaptation, or is that a place where you could use higher order elements, or how are you assuring to capture that higher gradient?
So we do some mesh refinement, and we will refine the mesh at those locations. And this is where biomesh is useful, because when we explicitly model that boundary, that allows us to hit finer elements there without putting it throughout the whole model. Whereas if you wanted a really coarse model, you could do something like higher order element, I suppose. Brian? Right, that's a good question. Now, the question is, what is the intended result that you want to get from the simulation, right? I've shown that these models aren't perfectly accurate in every aspect, but yet they're still valid in at some level. And particularly some of these full reaction diffusion models, I know the Trinova group has started using these in the clinic to help researchers identify regions that are susceptible to arrhythmias and such things like that. And they're using very crude models that I consider to have a number of inaccuracies in them. So they don't have to be perfect in order to be useful, but they need to tell you you need to have a goal in mind for that specific simulation. So it's more of you need to know the exact question you want to answer with the simulation. So with these static bidomain simulations, I think we need to know a little bit more about exactly what this border zone looks like and how it relates to maybe the vasculature before we can actually start saying, yeah, these models are a good predictor of what we'd see in the clinic. So.
Now that you mentioned border zone, I have a couple questions.
Mm-hmm.
First one with border zone. If I remember correctly, you have quite a few parts that's perfused with contrast, right?
Mm-hmm.
What did those results tell you in terms of that the border zones? Are they more toward the smooth type that you're suggesting
Right.
here, or is it more of the sharp border?
So from the MRI, you can oftentimes clinicians will talk about border zones, and we'll be able to see them there. These usually have more to do with like an infarct border zone, a more well-developed border zone where there's actual structural changes. Unfortunately, the actual border zone we're looking at is very dynamic, and there's not really a way to capture this in the MRI. We've used some contrast agents to capture the perfusion bed, but there's some questions of whether or not that really gives us a good idea of the actual border of the ischemic region, because the heart has this kind of dynamic system where it steals blood from one place to give it to another place that is ischemic. And so what we want to do is we want to perhaps use something like a microspheres technique to help us identify some of these perfused areas.
Microspheres will also give you more of a perfusion and microvasculature-based kind of
Yeah.
perfusion bed. So I don't know if would that help solve the problem.
This is still in early phases of our discussion, but it may help. Yes.
My second question is, can you give us a sense of the number of subjects that you include in each study? Right now, it seems like, I don't know whether it's n equal to 1 or n equal to 100.
Okay.
How consistent your results are.
So for the border zone study, there was multiple simulations for only about 3 canine data sets. But in each one, we did several runs on that particular data set. So maybe 4 runs per data set and maybe 3 different canines. With the meshing, the conforming meshing, this wasn't really, we didn't compare necessarily directly back to the experimental data. And we did approximately 6 different scenarios, variations of the ischemic scenario. We also did infarct. We did a couple different reaction diffusion models. We also did 2 different defibrillation studies. So, and then the final sensitivity study, again, was just a single model, but we did it for 6 parameters. Well, 4 parameters.
More general. I had to go to